Okay, we'll go ahead and get started. Good morning, I'm Greg Conti. This is Sergey Bratus, and we've been taking a very hard look at inside binaries, inside binary objects, whether they be memory dumps, files, file systems, anywhere we find zeros and ones. And what we found is a great deal of structure, a great diversity of binary species, and I think the understanding of that will help you, whether you're a forensics engineer, a reverse engineer, a fuzzer, or a security researcher in general, understanding the building blocks of these binary objects, something that's between the data type, ints and longs and chars and all of that, and the object itself, like a Word document, a binary Word document or something. So we're going to focus, we've tried to document as many of these types as possible, put them into categories. We have ways in the talk to visually identify them, as well as statistically to identify them, so it can ideally be automated. And the ultimate goal is to help you do your jobs better, speed analysis, and gain insight.
Well, I have a bit of a personal history here. Greg was the one who put me up to it. He got me interested in visualization, in leveraging the power of just the naked eye when looking at the bits. Because when you get to see those bits flying by or scrolling by on the screen, you sort of kind of see the patterns, and you actually get to recognize the patterns. And if you shift the data around, then you see the patterns in the shifting. But all of this is tantalizingly close and yet really hard to actually use. So what we're trying to present today is ways to actually make it simpler and isolate a few visual primitives that will hopefully tell something useful about a piece of a binary at a glance, and give you a reference as to what this thing might be. It's not something that you wouldn't be able to do with more advanced tools or special scripts, but those things will cost you. Those things will cost you the time to run them, the time to pre-process the data. Here, the idea is to have a visual cue that's just right there, and to switch between those visual cues very, very fast.
Okay, good. For bonus points, who's the picture, the bug-eyed man in the picture? Charles Darwin, very good. They had some great photographs. So this is my disclaimer. Does anyone read Rot 13 natively? I know no one reads it anyway, so I thought I'd make it Rot 13.
Что это значит?
So anyway, we're here as free citizens and not the representatives of our employers. So we're going to be using several visualizations, this one most of all. If you think of any binary object, whether it be memory, network flow, a file system, it consists of numbers, zeros and ones, or bytes. So if you think of that sequence of bytes, in this example, 255, 108, 40, and so on, and you plot those into a graphical window from left to right. So the first byte in the file is the top left corner, the second byte in the file is the next byte to the right, and the third byte, and so on. And what we've done is mapped the color, the grayscale, to the byte value. So 0 is black, 255 is bright white, other byte values are shades in between. And the advantage there is you can play with these color mappings and do all sorts of things. But the idea is this allows you, when you compare a hex editor's window to a graphical window, you can see about 300 times more information, at least in a graphical way. Obviously a hex editor shows it in a textual way. But that allows you to see the structure. So let's take a look. So this is a Word document. I've snipped out 10 megs in the middle because I'll walk through. So at the top, that's where a Word 2003 document, that's what ASCII text looks like. The next region is a data structure, and then the white noise area in the middle is several compressed images. And if you look where that black line in the middle, the actual header, the data structure that's the header for each embedded image is visible between them. And then at the end, you see other structure. And for example, there's a table of Unicode URLs that are in the document and other data structures in there. The idea being, and it goes back to what I said at the beginning, that there's integers and longs and chars, and then there's Word documents. But really, these things, these jar files, these executables are all built upon these primitive fragments, these primitive types. That's what we're calling them. Things that are bigger than the basic programming data type, but smaller than, say, a container object. And let's just look at an example. So this tool should be on, we submitted it should be on your CD, although we have not checked. And it allows you to load the file and bring it up. So here, this is shell 32, DLL. And you can adjust the width as you see fit, and it'll resize it. So you can get to like an offset that makes, or a window size that makes sense, like the different data structures in there. And then you can play through it and see the various structures. At this point in the talk, don't worry about what these structures are. We're going to go through that, but the idea being just that there are numerous structures inside a file, and it's good to know what they are and know what they look like and so on. And then you can scroll through and so on. So anyway, yes, Sergey.
So if I may jump in at this point. It's really interesting how the structure of binary files is being completely ignored everywhere you go to get an undergraduate CS education. So how many different sections do you expect to find in your typical Unix utility?
Like
1, 2, 3, 4, 5.
You need ELF file?
Right?
ELF?
Yeah. Let's say ELF, right?
Number 4.
32. Thank you. 32. These are 32. So obviously there is text and data and some sort of a header, right? So you can find 4 quite easily. But in fact, if you look from section to section, if you look at the section table, in the modern 32-bit, 64-bit machine, you will find about 32 sections in there. Some of those are symbol tables. The dynamic symbol tables account for at least 10 of those sections, all the sections that work together to give the dynamic linker that which it uses to link in the libraries. The symbol table, the string table, so some of the ASCII that you see as you scroll in there, and as you will see with the binviz tool. Then possibly even a hash table for lookups. But there are 32 different kinds of data that are different enough semantically that they have an entry into that table for their own. Just think about that, right? They are, well, some of them are code. Some of them are code that only works with this little bit of data, like the procedure linkage table that works with the global offset table. And the dynamic linker stitches this up when called. But there is a lot of diversity, even within a single executable file. There will be even more in the memory image when that file is loaded and executing.
So and just to have some other examples, this is a jar file. And again, don't worry about what the structures are, just note that there are different ones. This is an executable that Sergey was just discussing.
And we can actually see some of those sections right here. So this is the ELF header. What comes next is the section table. It's right there in, and it's it's offsets into the file, packed close together. Then you will see code, and you will see data, and hopefully, most of this is code. But there are also strings that go into dynamically linking the file, and there are all sorts of versioning information. And if your executable is not stripped, then there's a symbol table and other kind of debugging information closer to the end. But all of those things, I mean, these 30 to 32 sections laid out, and you can actually make them out very easily. And you can actually make them out even more easily before the file has been linked together, because you've got runs of zeros where the addresses of the functions would go. So, and
the same goes for system memory. This is from the Digital Forensics Research Workshop data set that they released this year. It's a Sony Ericsson K800. It's just a snippet from memory. And even network traffic, right? So this is a byte plot, but except that it shows one packet per line and kind of does a carriage return. So the long lines were large packets, the short lines are small packets. But again, this structure exists. And that we argue the current tools, things like grep and strings, hex editors for this general purpose problem, just they're insufficient. We can do better, and that's what we're trying to get at. And alluded to this at the beginning, that you're going to encounter unknown, unfamiliar structures. Typically, you'll be looking at them in text. And what we're trying to do by getting our arms around all the various types of building blocks, primitive types out there, we can help facilitate deep understanding, help you as a reverser, as a fuzzer, as a forensics analyst. And we're working on something called memory mapping. And the idea is if you can programmatically identify each of these primitive types, then you can write a program that dumps out. And here's an example. This is a memory map. Not the binary mapping. For bonus points, what is this the memory map of? Commodore. I heard Commodore 64. This is Commodore 64 memory map, but it was the intuition.
Glorious 8-bit address
yes,
space.
Beautiful. So the idea, though, and so from that memory map to this idea of binary mapping, that if you have the ability, then if you understand what these fragment types are, or primitive types are, you can identify where they begin and end within a file, and from there you can toggle them on and off and say, only show me text, or I don't care about text, or show me only code, or I don't care about code, and slice through the file, removing a layer at a time of this unknown thing you're trying to analyze. That's the idea. Another idea is that you can embed, we get our arms around this, we can embed it in things like a hex editor or mocked up there's a strings tab within IDA. You could have a compressed tab, an encoded tab, bitmap, audio, as you have this ability to identify these things. This is a taxonomy. It's the tree of programming languages. And I thought it was very useful to just show that this thing could grow without bounds. There's many, many different interpretations or variations of binary, of primitive types. So the idea then is we had to draw our arms around it and kind of scope what we did, otherwise it would spiral off into this incredibly unsolvable problem. So what we've done is kind of define the root of the tree and of things that you're likely to encounter, and went into a certain level of depth here and more depth in the white paper that we released. Okay.
So I would like to make a disclaimer. It's impossible by looking at a run of bytes to tell what those bytes are, what they do, what format they belong to. It's really, really very, very hard, and it's provably hard. Okay. However, most of the time, we are not looking at those incredibly disguised things such as shellcode that is supposed to be the English text. Such a thing has been done. We'll mention it as we bow out. But most of the time, you want to know what the hell is it that you're looking at. Is that a compressed stretch of bytes? Is that something that might be media? Is that something that's likely to be code? So, one of the great things about IDA is that, well, it's interactive, right? You get some heuristics to actually try to guess what a segment is, and then if you didn't guess right, you can annotate it as code, and you will have a disassembler run over it and do the smart thing. But wouldn't it be nice if you could say, here is something that I think is compressed with gzip, or with this or that compressor. Or here is something that's just likely to be encoded text. Can we detect the boundaries of that? And so on and so forth. And so it's really just about this. Before we got the DNA as the foundation for classifying species, all that an explorer could do was go out there, catch an animal, check its foot or tail or beak, and drag enough of those animals back and try to systematize what the hell they were. I mean, the whole idea of the species started before Charles Darwin with Carlos Linnaeus and others, but the very idea that, some of those things were not like the others and yet similar. So a descriptive nature of biology, a descriptive nature of classifying species, that played its role. It was useful. It helped us understand deeper things about the species. So here we are, right? We've got all of those little creatures, some of them slimy, some of them wormy, some of them, with little arms and legs. And they're crawling around in the binaries, and you pick one up, and you look at it, right? And what is it? How can you try to classify quickly what it is? Now, if you're a biologist, right, and you've caught yourself an animal, well, you know to go for the hooves, right? That will give you a large part of the classification already. Then you look at the, well, not really, not the tail. Then you look at some other distinguishing features, and finally, I've got myself a chimera. So the thing that will enable this development, we believe, is a classification, a dictionary of types. And then, once we assemble that, and we have a whole bunch of binary fragments from a whole bunch of different types of files that we think are a reasonable first cut at such a classification, then we can apply very simple visual checks. How many wings? What length the beak? Split hoof or what? Right? So that is the purpose of what we are going to do. And for that, we need to come to an agreement what a primitive type is. So not something very long, not something very short, right? Not just your basic integer, because how do you visually recognize an integer? You can visually recognize a small integer. You can search for structs in memory that are known to contain small integers. If you're looking for your proc structures or your process structure in the Windows kernel memory to locate your rootkit, right? This is to locate process structures that shouldn't be there. But that's a different thing. These things are quite large. They may be kilobytes large. We want something smaller. On the other hand, we don't want to say that the doc file is a primitive type. Gosh, no. That thing can contain everything in the kitchen sink. We can't say that a PE file, an ELF file, is a primitive type, because, again, that thing is made out of many, many parts. So we need to make a design decision here.
So I think Sergey alluded to it. What we had to do is come up with a reasonable approximation of what is too small, what is too large, and we'll show you as the decisions as we went along the way. But one thing to think about is if you think of a simple file, there's an image file, might have a header and then a payload. We consider those two different things. For example, the header we consider a data structure because maybe you want to be able to find data structures within a file. And then the payload may be a bitmap, it may be a compressed image. And they're distinct. The header and payload are distinct. And also we had to come to grips with that many types of encryption, compression, and encoding occur in this binary jungle that's out there, zoo that's out there. And how do we incorporate that into thinking about this problem? As well as potentially artifacts, like in an image file. In a compression scheme, there may be markers or something embedded very closely, very small markers. Are they considered part of that image or that compressed block, or are they something else?
So there is a disclaimer here. Again, you can bring on any custom transformation that will completely disguise the nature of the file. However, I mean, you can pack a virtual machine that actually regenerates your file, just the same, your actual content, just the same way as Dwarf does in many of the things it does. But again, your typical shell code doesn't usually come with a virtual machine. Most of the time, it comes in XOR obfuscated, or added has the same number, or the same 2-byte or 4-byte integer added to each word of the shell code. So through those transformations, we should be able to see, and we can.
Okay, so in the paper we go into lower levels, but the highest level of this categorization is what you see on the left, the idea of these primitive types. And to think about this problem, we looked at the MIME media extensions. There's several registered, the IANA registered media types. Some analytic tools have binary templates, and then container file formats and the like. So we took a hard look at those. This is the highest level. Again, the paper goes into significantly more detail below each of these. You can envision text getting into different encoding schemes, then each of those being different human languages, for example. And the general approach we suggest in trying to identify these things, alluding to the identifying chimera, we have the byte plot view, which we showed, obviously looking at hex and ASCII. And we also present two other, the idea of looking at a frequency histogram of the bytes and the digraphs, the two-letter sequences, two value sequences appearing in the file. And then comparing those to dictionary of other similar structures. And this is the analytic approach, but we also suggest you will gain insights, and with those insights, you're going to find like statistical outliers or ways these things stick out, and with those you can find automated ways to identify them.
So think of it as a bunch of antique magnifying glasses. So you're on the Beagle, you've just acquired this creature, you bring them out, and you look at it through this one looking glass and say, doesn't look like anything I know. Take out another one very quickly, again, look at it through that one and say, all I can see through that looking glass is the hoof, or a part of the tail, or that strange glowing bit. But I know what that looks like because I've seen that sort of thing before. So it's really about the visual transformations of those primitive pieces that nuke some or almost all of the structure out of what you're viewing, but make the rest look familiar, make the rest look recognizable. And biplots and digraphs in particular will be very helpful.
So as we go through these examples, I'd ask you to think about, okay, we're looking at visually what stands out, but think about how it could be done algorithmically, because ultimately the future lies in the people in this room don't scale all that well. So if we can capture your insights in an automated way, then there's the real power, and that can be handed off to machines to do the grunt work. So even in the text category, you can see, and with these, again, just recognize that the structure is different. And that, everyone in this room, or many people in this room, could write little scripts that could identify these independently, because there's nice handles that you can get your arms around. But again, within the text arena, a great deal of diversity. So what we're going to introduce here is the idea of the digraph view. So thinking about that, if you take the word black hat, the digraphs are the first two letters, BL. The next digraph is LA. The next digraph is AC. And so BL is, lowercase bl, is 98 and 108 in US ASCII. And then LA is 108.97. And so you get these pairings, these pairs of values. And by plotting these pairs of values, you gain a quick insight into the contents of a given file or a sliding window within a file. And that's what we do, which we'll get to in a second.
So for you language aficionados, programming languages aficionados out there, this is simply a bigram model of the language that is the binary. So you can think of modeling a language as recording which word follows which word, which byte in this particular case follows which byte. And you can have a table of such pairs that you observe. They're called bigrams. And you can actually generate pseudo-English or something very close at the first glance, or at the first hearing probably, I don't know. If I start sputtering gibberish, you know that sort of a circuit switched on in my brain. So the dissociated present Emacs, the Markov models of natural language, that is the same idea. So you record the tuples, you record the bigrams.
Okay. So just looking at ASCII text. So this is the top right is this part is just a picture of it. That's the histogram, and you can see the large values near the middle. That's the lowercase characters. The long vertical line reaching all the way to the top is the space character. We started off with text because I think everybody can kind of get their head around that pretty readily. And then this is the bigraph plot. This digraph. So this plot, this is what ASCII text looks like. This is where it falls into. What do you think that bright region in the bottom right corner is? Yeah, lowercase characters. So that's lowercase characters, sequence pairs of lowercase characters. But you'll get to the left, you'll get uppercase and then a lowercase. So you're going to see, essentially, that's a very distinct signature. And when you're looking at a binary, this will pop out at you when you hit text. And Unicode. Okay.
Question?
Yes.
On that, did you do anything to represent the frequency of occurrence? Is it more frequent or brighter, less frequent or different?
This just shows presence on the left, yeah. And you could do that. You could color code it. For this, it's just on or off. And you have to make a decision like how far ahead do you look? Do you run the entire file through this? Then you'd have different fragment types overlapping. So we took a sliding window approach.
Yes. In fact, we do have a frequency of occurrence later for a different method.
So I'm just loading a text file now. And not all that interesting, but you can see it's got, this is just a large Project Gutenberg text file. One thing that we also have in the tool is an entropy plot. So it plots alongside the entropy. So you can see that the entropy of English text, and it corresponds with the line at the same level, is about 4.2, something like that, 0 to 8 bytes, 8 being the most random or most unpredictable. And then bitmaps. So bitmaps can exist on a file, although they're uncommon. Typically, they're compressed. Importantly, though, they can exist in memory. And when a program loads a compressed file in the memory, typically it decompresses it. And we've looked at memory dumps and things like that, and you can see the bitmaps residing in there. Now, the problem with bitmaps is that where text is a very tight knot of what you could expect statistically. Bitmaps can be anything. You could have a bitmap of white noise, or you could have a bitmap of a black square. So when you're doing this, though, common bitmaps, and that's where we have to go to commonly, what will you run into? Those show, those stand out. Yes?
Will that work with steganography?
We have a steganography example in here. I would say it'll work with some. Right? There's some very, certain naive, the example we have flips lower bits, least significant bits, that shows up. But there's some very subtle techniques in current steg. Sure. Okay, so the top right is a bitmap. Now that's not the looking at it with an image viewer, that's looking at it as a byte plot. So because the window, the byte plot doesn't exactly represent, it's not an image viewer, it's looking at the raw bytes in the file. That's what it'll look like, or it can. That's the histogram for that particular bitmap. But the digraphs, particularly in normal photographs, normal images, will often look like fireworks in the digraph.
And you can see the structure, which is very different from what it was in case of the text. Even if this were SOR encoded or shifted in some way, the picture would look the same. It would just shift around in that view. And that is the power of a simple visualization primitive. So that's your, antique lens number one.
So here we're looking at 3. The bottom left corner, if I get it right, you can start kind of seeing it. So the bottom, this on the here, this part is the digraph view. Off here to this side is the entropy view. Yes.
On the entropy view, how do you scale that vertically? You get 1 entropy reading for the entire file.
It's 1 entropy reading per line. So, and right now it's fixed to the default. So here, it comes out at 640 by 480 in the byte plot view. So each line of this byte plot equates to the location of the entropy.
Yeah.
If you resize this, the byte plot view, the entropy doesn't resize along with it.
Yeah. For entropy, you need a distribution. So you just decide on the window in which you take that distribution.
And yeah, I mean, there are many ways you could do it. You could add tuning knobs to all of these things. But then as you go through the file, you can see that this, that changes as you go. Okay. And again, this is just one example. But what we found, we've looked at a lot of examples, and what we're showing you are things that we've seen appear time and time again. So we're not suggesting these weird one-off examples, unless we tell you it's a weird one-off example.
Yeah.
Here's a weird one-off example. To the left is, to the left is a picture, and inside that picture, in the 2 least significant bytes, is another picture. All right, so of a cat, and all cats are named Mr. Jingles, so that's Mr. Jingles. And here's the view. So what do you notice about it? Actually, let me make it bigger. Okay, you can see something weird going on here. So for the person who asked the Steg question, manipulating lower order bits, if you've got 2 levels of things, yeah, it may very well show up. It depends on, again, it depends how much you're putting in there and how similar the things are, but you've got a good chance.
Yeah. So it's a familiar beak, but it also is something else. It can probably open beer bottles.
And there's but there's many different image formats. So there's a great deal of depth as you think through this of ways images can be, if you want to identify them programmatically, for example, or try to, there's different ways they're encoded. So you have to think those through. Audio is another good example. Again, it can be compressed, but it has to be uncompressed at some point to actually typically be used. So here's an example. This is a WAV file. Notice the U-shaped, the very distinct high and low bytes for a WAV file. And this is a 44 kilohertz, 16-bit per channel PCM encoded audio. And here, the digraph's very distinct. And this is Sweet Home Alabama. And sadly, when you press the play button on this, it doesn't actually play the song. Okay, so you can see there is structure. It's a different structure. You're not going to get a picture emerge. And then the entropy does change. But I'm going to hit play here. And actually, I'll probably speed this up. See, it changes pretty significantly as you go through. So the idea is, with these insights, how can you programmatically identify these things? Now we know the digraph has that characteristic. And you can see the entropy as well. Now, these are pure fragments, so we're not looking at mix. We're looking at individual primitive types here, essentially.
But you could take a sample out of a larger file and quickly categorize those samples, even if the file were, for example, XORed.
Yes, or the BinViz tool will allow you can just slide to that offset and take a look. Compressed audio, and this is a theme you're going to see again and again. Compressed audio and encrypted and random numbers typically exhibit very little structure as they're intended. But if you think about the nature of each of those categories, compression typically wants to be reversed, right? It's a reversible process. Encryption wasn't designed to be a random number generator, so there are perhaps some statistical characteristics that distinguish it from random numbers themselves. And just taking a look at this MP3, there is some structure there. And looking at it, and this is a view I just want to touch on briefly. It's Dan Kaminsky used it. It's called the dot plot. The link to the original paper, and then Dan Kaminsky's talk there. But the basic idea is it's a measure of self-similarity, a measure of structure within a file. And if you take a sequence of values, byte values or words, here to be or not to be, and you plot them on the horizontal and vertical axes, where they coincide, where 2 appears in, the same word appears on both axes, you plot a point. That's the basic idea.
So just like the digraphs are a measure of bigrams, this is a measure of self-similarity.
And this is the MP3, and you see there is structure in there. You might not notice it with eye. You almost certainly won't recognize it with a hex editor, or you might not. So anyway, these are just, again, once you've found that, you say, well, what caused that? And you can kind of narrow it down and then maybe find a way to use that to your advantage. Video is essentially sequence, uncompressed video, full-frame video, just is the AVI format's just image after image, like a flip book. Compressed images often will have a keyframe, which is a full frame, and then followed by some sequence of frames that just show the difference, followed by the keyframe. So this is just looking inside a compressed AVI. And again, it's useful to see these pictures, so as you're looking at these things, you can't really tell this from a hex editor. Windows PE file. Now this, we won't say it's the same primitive type in there. I mean, if you look at the text region, at the bottom, there's a table of strings, so mixed with the code at the top. So the text at the top is what code looks like typically, and then in the resource section, our SRC section has bitmaps and other different types of structure embedded. So but it's useful to. I thought it'd be interesting to actually see what the sections looked like, because you spend a lot of your time in those sections, and then looking at this command.exe as well. So now looking specifically at machine code, we looked at a lot, and we have some statistical analyses at the end. This is just one example. But you get a histogram or a digraph plot that looks kind of like a grid. So if you're going through this file and you see that grid appear, that tells you that it may be machine code, because we found that there's not all that many common primitive types out there that once you get a handle of what they look like, you can start identifying them on the fly. This is the ever-popular calc.exe, probably the most analyzed program in the world. Okay, so at the top, so as we play this, note, so this is the grid that I was discussing. You'll see that grid, and this top part, the top half of the file is essentially all grid. And you can see that's what it looks like. And then as you transition, you'll see it popped briefly when it hit strings.
Yeah, by the way, you just saw a piece of text, which is the
right there.
Which
so
is your
that's,
string table.
that's the string table. And then you get into the images that look like fireworks, right? So you get the fireworks kind of at the end. And this is, as we said, bitmaps could be anything. Data structures, typically you know them when you see them. Oftentimes they'll be blanks. They have a great deal of structure, pardon the pun, but they're visually very recognizable, but they could theoretically contain random numbers. So they but in common practice, they look like this. So what are the statistical signatures like? Is there a way that you can pull out data structures? And as you'll note that we're not talking about knowing a priori the file format in advance, we're not assuming any knowledge. You could combine that with certain knowledge if you know a file format, what should be expected at a given spot, but we're not assuming that. And again, random numbers look like random numbers. The flip side of random numbers, padding, repeating values, and the like are again very easy. But you do see that, so we included that in our thinking about this problem. And then there's the idea of transformation. So we've largely looked at kind of the raw, the base primitive types, but they can undergo many, many transformations. Some encryption, compression, and coding being the most common. And if you think about an image on a camera, maybe an uncompressed image, a TIFF file or something like that, and you load it onto your computer, you load it into Image Editor, you edit it, you save it as a compressed version. That compressed version may be sent over a protocol that uses encoding, text encoding. So these transformations occur. When that compressed image is loaded into memory, it's uncompressed. So it's going to, what one thing we'll like at different points in this game will be different, but oftentimes you can find some signatures will often pop through. So this is just a Windows PE file that's base64 encoded, and you can see the text region at the top still is visible, and also the vertical lines there you see that as a common artifact within base64 encoded files. Sometimes other artifacts like this chunk here, I drew diagonal lines on the top and then there's a mirror image on the bottom, that there may be artifacts in there that you didn't know and that you can use to your advantage. This is a UPX file, I think a compressed file, I think it's cmd.exe. And at the top though, by default it only compressed the code region and the other structures there. So you can see a kind of certain times structure pops through.
And this code would not look like the code in the byte plot.
Yeah, it would look like a compressed, more like the white noise, the star field kind of look. And then encrypted looks a lot like random. And then it's also useful to think in terms of the obfuscation techniques people will do within their code. And there's a wide variety people can use. We've chosen just a couple of examples to illustrate. If you adding and subtracting a constant, looking at a hex editor, things will look different, right? But other properties shine through with the right magnifying glass, the right window. So here's one that we've shifted each by 150 and wrapped around if it exceeded 255. And by adding a constant, it's useful to think of that as a shift cipher, right? That you're just shifting two alphabets side by side. But in the frequency distribution, still in the same order, it's just slid and you just shifted it. And the same thing, like XORing a file, XORing value. So you've got a key, a randomly chosen key that you're XORing with every value, 8-bit XOR. Yields a set of values. But depending on the key you choose, there can be any mapping between the plain and cipher. So this 8-bit key is really the equivalent of a monoalphabetic substitution cipher. But still, structure pops through that because even with a limited number, with one key like that, there's a reason why one-time pads have an infinite, or have a key applied, a random value XORed with every value in a file, because otherwise structure pops through. So anyway, thinking from 8-bit XOR to 16-bit XOR, you have 16 bits. So the first 8 bits is key 1 applied to byte 1, and applied to the second 8 goes to byte 2, and then you reuse the keys. And essentially what you've got is a 2-alphabet polyalphabetic, I'm losing my mind.
Yeah,
There.
one of those.
Yeah, polyalphabetic. So you've got a 2-alphabet polyalphabetic cipher. And if you've done 32-bit XOR, you have 4 bytes, essentially, and you keep using, or 4 keys, and you're reusing those. So essentially you have 4 alphabets.
So what you'll see on the diagram, for example, is that you'll be seeing double or quadruple of the usual picture, but it will still be the usual picture, because neither of those methods actually destroys your bigrams. It transforms them, makes them into different bigrams, but does not destroy them entirely.
Sure. And then, as I mentioned before, that if your number of keys go all the way up to match the number of bytes, then you hit a one-time pad. So what you're talking about, those values become more and more diffused as you increase the size of the key. And I think so. Demo time.
So let's see that.
Okay, so I'm not going to tell you what these are, so you have to tell me what they are. Okay. So the byte plot, what does that look like? It looks kind of text-like, okay, and I'll get so that is correct. And then if you adjust the size, you get lined up right. What do you see in the middle? Yeah, you can see vertical bars. But look at the digraph plot. Remember, if it was all uppercase and all lowercase, you should just have the lower right block being the common digraphs. But we're seeing digraphs of many pairs within the printable ASCII range. Bing, good. This is base 64 encoding. Open. Okay, so the first part is, you see, what does this indicate? The digraph view indicates what? Yeah, now we're doing something here though, and actually let me do this. Okay, as I slide through the file, it's shifting. So think back to the adding and subtracting a constant as a simple encoding technique. So here we've added 0. If you go through the file, like say in this bottom right corner, we've added 255 to every value. So what it's done is shifted it all the way to the right. So again, this shows you that just simply adding or subtracting a value, it's kind of like a known plain text attack, right? You know it's ASCII text going in. If you try and obscure it with just a simple adding or subtracting a constant, remember shift cipher, it just shifts, literally shifts the digraph.
So here's a looking glass that sees through that obfuscation.
Yeah, and then as you slide, you can notice as you go through the file, it gets brighter and brighter because it's getting higher and higher order bits until it wraps around, and then back down. Okay. So what we've done here is, you see this rainbow effect. We've applied a key to each of those, an 8-bit key. 8-bit XOR. So we've chosen a random 8-bit key and applied it to, I think it's 20 lines at a time. So you can see this rainbow effect where it's chosen to XOR a different range. But as you play this, you can see that the structure still is there. You've done 8-bit XOR, and it's still, regardless of the key, where this is like exhaustively going through the entire key space, and you can see that each of the potential keys still has a distinct structure shining through. And part of it is there's that one region, that darker block, that, here it's in the top left, that you can think about that. Given the key that was chosen, the input was very high in a certain range, 32 to 127, but actually probably lowercase letters, that range is what shines through. And then even if you do 16-bit XOR, so it's just 2 alphabets, right? So when the keys, you can see the 2 alphabets here popping through in this attractor. I'm sorry. Gosh. So you can see the 2. One key had the effect of shifting it here. The other key put it down in the lower left quadrant. And then as you play through and different keys are chosen, they show up in different places. So this is an indicator of text being XORed with a 16-bit key.
Yeah, you would get the same effect if you composed 2 very different languages that have their own natural digraph structure, natural bigram structure, but they just simply don't mesh. Either that or you're seeing double.
So this one's a little different. When I coded it, I forgot to do one thing. So when I wrote this, I intended, okay, this is going to be 32-bit XOR. But as it turns out, I only made, it's really 24-bit XOR, and the last key, the fourth value was 0. So what you see then are these vertical lines here. All right, see the vertical lines, that's because every 4th byte value is 0. And I confirmed that by looking at it. But anyway, it showed you something was amiss. That even when we play this, though, this is essentially 24-bit XOR. You can see the different alphabets still popping through the key, or popping through the obfuscation technique. and it might be hard to see, but at the digraph, if you think about if one of the keys is 0, you've got digraphs here then. So, I'm sorry, not if one of the keys is 0. Yeah, you get digraphs of
The bytes of the key.
yeah, the bytes of the key at the top and at the bottom. Okay, I think that was it for these. Okay, so I think
Let's go on.
yeah. So we've shown you visually what this looks like. Now each of these lines is 1,000 samples as pure as we could make them of that given type. So at the top, we have random examples, encrypted examples, compressed examples, and the left red box is average byte value. The right line or right box is the entropy, Shannon entropy. So what we have is so you see high entropy, this cluster, and then but you notice that there's statistically difference between the encoded version, still high entropy. We encoded zip files, but the average byte values are significantly different. Machine code, again, significantly different. Bitmaps, but with bitmaps, recall that they could be anything, so they're very diverse in our samples, and the standard deviation there is 69, which is huge, which means it's all over the place. And then text, again, a pretty consistent view. So we plotted those, one entropy versus byte value. And the idea is there's intuition here that we can programmatically detect some of these things. You've got, now the high entropy cluster, it's really hard. That's a non-trivial problem to pull that apart. But as a unit, the idea of high entropy, that can be detected pretty straightforward. Pulling out the base 64 encoding and UU encoding, pretty straightforward from our experiments. Of course, there's going to be noise and there's going to be things, unanticipated things. Machine code stands out, ASCII text and bitmaps. And it would be interesting in the future to draw these boxes based on the standard deviations, kind of get a feel for how big each region is. It's a little bit bigger or smaller than the marker that we've used.
So, and these are only two possible statistics that you can throw at the thing. They're really, and they're really well known, well understood and simple. Now imagine what you can do if you take an aggregate of 10 or more statistics. What kind of clusters would emerge? Some of those actually do catch the artifacts of compression and of particular kinds of encryption, especially if the key is not chosen wisely and if proper padding is not applied. So you might actually be able to visually detect encryption with a key that wasn't chosen properly, or with a key or where the right padding scheme was not used. Now let's do something else. Let's try to see visually how some things are like the others and others are not. The inspiration here is this wonderful work done by two physicists who managed to reproduce almost entirely the phylogenetic tree of languages by taking the Universal Declaration of Human Rights in every language in which it was written and compressing those files together and separately, and noticing how much better they actually compress together. The idea being that while you're compressing one file, you are already working up a string table, and that string table helps you compress the other file better. And so this is what we did to binary fragments. And you get those bathroom tile kind of pictures, where you have many fragments of different types. You group them, and then you see how well or what the compressed file would look like. So in this byte plot, I'm taking a Linux x86 executable and compressing it with the rest of the x86 Linux executables, so it's home team, so to say. And instead of collapsing the strings that are in my string table for compression, which is how the Lempel zip compression works, instead of collapsing them, I color them in their entirety with the color that the darker it is, the more frequent that string, the more frequently that string is known to appear in that corpus. And so you see that there are pretty long runs of strings that were found. So those are verbatim repeated in other files like that. Whereas if I compress it with my bunch of bitmaps, it doesn't look so good. In fact, I don't get long blocks at all. I get short blocks, and some of those are just bytes, which means I ran out of my string table, and I am not seeing the same strings that I was seeing when I was generating the string table. Now, some of those things are more like the others. This is the executable code compressed with music. And you see certain periodic structure. These things actually occur in code as well. But they're not long, and their distribution is strange. So these are those triples that, could be executable code. So I'm going to show that with luck. I'm going to show that live. Do we have the time? A couple of minutes. Let's see if this works. If this doesn't, then we'll give you the demo. Okay. Shall we attempt this? All right, great. Great. Oh, right. Okay. This is a very visual cat. It's ogling the binaries. Sorry. All right. So here is a particular bit of binary code compressed with its native data set. Here is the bitmap that we've seen. How does it look when I compress it with bzipped text? Well, again, not so good. What happens if I compress it with encrypted text samples? Again, you don't see any long blocks here. And so you can go through the different kinds and see where you're getting longer runs that are common to that data set. Let's look at the windows. So it's not quite the home Tim, but not quite the antagonist. And you actually see a little bit of similarity here. Some of those, some of those byte runs generated by the compiler are like the others, and some are not. And so you can, this is a little processing application. This is the music example. And so it goes. Compressing things together with random files does not help much because you don't get to see much of the similarity. Right? So that way, you can very quickly spot sharing of substrings, byte substrings, between two files. So, and this is nothing but a very simple Lempo-Ziv compression with counting of the occurrences, the frequency of the occurrences of the strings in the table. And let's go back to A.
Okay, good. So we just to kind of recap, we showed you the insight that we saw visually, the statistical outliers, and then the fact that there are statistical differences, and you can use statistical signatures, you can use what Sergey basically is a compression-based classifier, and other techniques. So thinking about this, as we move forward, obviously there's the bitmap diversity and data structure diversity problem, that they could be anything. But we believe in practice they typically aren't there's enough similarity there that they could be identified. That cluster of high entropy types, it's hard to separate those, particularly in small sizes. I think we've gotten following things as they're transformed. Sometimes the transformation is so severe nothing really shows through. Other times it does, like in our examples. And also like to, actually you were going to comment on the obfuscation.
Yes. So it is the technique. It is well known that you can disguise things. So my favorite disguising tool, early disguising tool, is John Erickson's dissembler, which takes shellcode and translates it into ASCII-only shellcode so that the byte codes are just printable ASCII. Recently, that a similar thing, but with an enormous amount of overkill, has been done by this academic group. They actually not only made it printable, they made it sort of indistinguishable from English text by assembling those printable instructions into words, English words, then compensating for the side effects of those instructions, and the whole thing took hours, many hours on a cluster to fit the purpose of that shellcode. And in the end, you have a short essay that kind of sort of makes, well, no, it doesn't make sense. Yes, it does actually, well, it's more like a postmodern thing. But it is actually runnable shellcode, which blunders in doing what it does, but gets there. So you can make data look like, you can make code look like data, you can make data look like code. If you have to throw, if you throw enough computational power at it, it's possible to obfuscate things to hell. But nevertheless, normal code, normal data that even malcode that is in commercial production doesn't have to do that as an engineering necessity. And you know, you look at the shellcode out there, you don't see that much of very, very deep obfuscation there as well. So it's not all XOR, but it's certainly a lot of XOR. So we have this talk, we have the underlying classification in this paper. Well, this is really something of an academic paper. You will find it on your CDs as our white paper to go with our talk. And we try to go a lot deeper into the classification of those binary fragments. And we try to distinguish them by simple transformations that discard all but the most showing of that structure, as we, you know, those looking glasses, those magnifying glasses that we've tried to convince you work. And then for the future.
So again, just kind of the theme that there's the potential here then for automated identification. The idea of using classification techniques, clustering techniques, data mining techniques, combining all of that to combine some way to have automation helpful. You could incorporate you know, knowledge about what comes before, some probabilistic knowledge, like one data type typically follows, one primitive type typically follows another primitive type, or known offsets in a file format. It'd be nice to extend the set. And I like the idea of memory map, a tool that you can just pour any binary at, and it'll give you its best guess at what the map is, preferably with a plug-in architecture. So we're going to be wandering around Black Hat and DEF CON. We welcome feedback. I think it'd be interesting, some of those people have obfuscated shellcode, like those English shellcode. I think it'd be fun to see what that looks like. I haven't done that, but I bet it would show kind of this hybrid characteristic of the machine code view and the and what ASCII looks like. So it could be interesting for someone who wants to take a look at that. So if the white paper, we actually put a lot of thought and effort into that. So it should be on the CD. If not, we're happy to get it to you. We'll have it up on the web shortly. And then there's some our set of CDs, again, should be on the web, on the disk. that has the slides, so you don't have to copy it down. But we've been working this theme for a couple of years now, and this is the latest evolution of where it is. So there's some previous work that might be interesting. The BinViz tool that we used, the source code and executable should be on your CD. If not, we'll have it up on the web shortly. And I wanted to point out that Marius, and I can't pronounce his last name, Wishy, has done some work extending BinViz, an earlier version of it, as a Google Code project, so to work cross-platform was his intent. I'm not sure where it stands, and I haven't personally used it, but I did want to tell you that's out there. We also like to thank our co-authors on the white paper. And with that, did you want to invite? Okay, let's go ahead and take questions.
Yep.
You're defining primitives, and you're showing how those visually are coming out. Is there any interest, or you've had future research towards finding easily definable structures within the primitive? In other words, you have a code block, but you would define like this is a type of code, and this is a different type of code, or this is a different seed, and now all of a sudden you have blocks that are written in assembly.
That's quite possible, yes. We tried to isolate the purest, what we judge to be the purest examples, but certainly, as with your typical biological classification, as it used to be done before you could actually sequence DNA, the boundaries are blurry. And you can define subspecies. In fact, you can get in a fight with other biologists over whether this is a subspecies or just a local variety. So what we wanted to do was to basically give you the tools to try looking at whatever data you are working with, so that you would develop this intuition for what the basic types are and what they look like in those plots that suppress out most of their structure but keep something that's characteristic of that particular type, like the digraph or like the zip thing. Yes?
One thing that'd be interesting to see, so a lot of malware tends to inherit from its predecessors. Something which release security. It would be really interesting to see if there was a tree based on this. Essentially the inheritance of the taxonomy of malware.
Yes, so I know, this is a wonderful question. It has finally propagated to the larger academic mindset that much of the code that is written now is actually written by mutation of existing code. And Oliver Couch has a really nice article in the Usenix login on programming with ritual and alchemy, which is a wonderful name, which is basically, you get some code off of the web, as an example, you paste it in. It kind of works. You go on the web, for example, for how to fix it so that it actually does work. And this is as removed from good practices as possible. This is as removed from what people actually teach as good practices as possible. However, he found himself doing that with a particular version of Hadoop that they wanted for a research paper, and so hence the programming with ritual and alchemy. So there is quite a lot of code floating around, and there are better metrics than just mutual compression to throw at it. In fact, I think I know a thesis that is looking, a student who is looking into this in his thesis. I'm not sure how much I can say, but if you are interested in this, please contact me. I'll put you in contact with them. But definitely, there is a lot of mutation of code going on through us cut and pasting humans.
Have you tried looking at larger values, like plotting, like keywords, like 32-bit values sequentially is their position to be executable?
Well, what we've done is up to 24 bits, plotting, well, there's a view in there, red, green, and blue to a given, so the first 8 bits is to red, the second 8 bits is to green, and then the last 8 bits is blue. We haven't tried above that, but I think ideally I think where we're heading with, I think where we're heading with this is something that can handle anything from 1 bit up to n bytes, right? And you can change the views to look at whatever layer you want, and because it isn't an 8-bit boundary world, and it would be nice to be able to tune, set arbitrary boundaries as you explore these things.
I usually like the photograph, and like if you had a graph of like the position, like y being the numerical value of that 32-bit integer. If you try that, you get some interesting patterns with pointers.
Yes. So we were looking into this, and we were looking into what may be offsets as well. We applied this to captured memory on Solaris, as it happened, because of dtrace. It's very fun, and there are definitely structures there. They are not the primitive structures in that they're not local. They're, it's hard to just take a snapshot of a piece of memory, a small piece of memory, and suppress it down to something like the digraph and see them. But there is definitely a structure, and you can see heaps, for example, they stand out. You can see slabs, they stand out. Let's see, I should have given, I will put the pointer to that project, to that student. Again, it's a student project. I will put that project, pointer to that project online. So yeah, we hesitated to bring that here because, first of all, it doesn't really fit with the binary, with the primitive fragments kind of thing. And secondly, there are other people like Denny Quist looking at graphs per se. So if you look at his recon talk or his previous recon talk or his talk here, he used a hypervisor to look at graph structures that you get to see at runtime. And pointers actually do play a role. All righty then. Well, yes?
Talk a little bit about using it to analyze network packets, but you didn't really show how to use the tool to do that.
So that would be the rainfall visualization that Greg came up with. Yes.
So we have done this for network packets as well. The project's older, so it was the RUMINT tool, RUMINT, has a view that will allow, that's where that one picture was generated. It has probably about 20 different views. I haven't worked on it in about 2 years, but it'll handle, well, I switched from network packets over to binaries, so it kind of evolved from there and went down this binary path. But it's out there and the source code's out there too, and it has a variety of different windows in there.
So the problem there is that with the packet, it's hard to determine what the peer group is. So for entropy measures to work, for example, you need to take a distribution. So taking a distribution over a single packet doesn't seem to work so well. So you need to get some idea of the session, but in fact, you're trying to discover what the session is. And so it's a little bit more tricky. But we're definitely planning to do something along these lines later. Let's see how successful we'll be. All right. Well, we're out of time. If you're interested in a graduate degree that disguises hacking as research, as academic research, consider Dartmouth. Consider our lab at Dartmouth. Well, here we go.